So far we've talked about that when two atoms interact with each other and they are both metals, because they have very few valence electrons, they abandon those valence electrons to create that sea of electrons, and we have the attraction between the positively charged cations that are created and that negatively charged sea of electrons, and it creates the metallic bond. Then we've looked at what happens when a metal and a nonmetal interact. And because metals have very few valence electrons and they want to lose them, nonmetals have a lot of valence electrons they want to gain, we wind up with a transfer of electrons from the metal to the nonmetal. This creates a cation and an anion, and they attract each other, and that creates the ionic bond. Now we're going to be starting to look at what happens when two nonmetals interact with each other. Nonmetals have lots of valence electrons, and what they would like to do is to gain a few to finish filling up those valence shells. The problem is that there's nowhere to get those electrons from. So what they end up doing is sharing their valence electrons. Any shared electrons can be counted then by both nuclei that is sharing the electrons. The shared electrons spend their time between the two nuclei. The atoms do arrange themselves into a lattice structure. So all of these different kinds of bonding, metallic, ionic, and now we're going to be looking at covalent network, they do create a lattice structure when they are in the solid state. We are going to be looking at this chart, and you have space there to make this, and so I will give you a moment to draw it before we talk about it. So one thing to notice about this picture is on the x-axis, what we are representing is the distance between the atoms, and on the y-axis, we are representing the potential energy in kilojoules per mole. Potential energy, remember, is the energy of position. When you raise something up off the ground, there is now a distance between the object and the earth, and so that object has increased its potential energy. So when we talk about potential energy, it's about the position relative to each other. This is also kind of a unique graph because it starts from the right, and we read it from right to left. I'm not exactly sure why they do it that way, but every textbook that I've seen that has this graph in it, it's always done in this way. So what these represent, and the explanation is down below. Okay, so this A down below is describing what's happening in what we have labeled as A up above. We have two individual non-metallic atoms, and they have some amount of potential energy. Notice that our chart does not have any actual numbers on there because this is representing any possible combination of nonmetals. And depending on the particular atoms, they would have a certain potential energy, but we want it to be a more generic representation. In picture A, the atoms are far enough apart that they are not interacting with each other. They are existing as individual atoms. As they move around, they may come in close enough proximity to each other that there start to be some attractive forces that affect them. We have the positively charged nucleus of one atom that is attracted to the negatively charged electron of the other atom. And that would be true vice versa also. This nucleus attracted to this electron. So that's an attractive force. But we also have the outer electrons, because they have the same charge, they are repelling each other. So we have these two forces that are starting to affect the position of these atoms. So the nucleus of one atom is attracted to the electrons in another atom, and vice versa. There are also repulsive forces of the electrons in the two different atoms. And to start with, the attractive force is strong. It's stronger than that repulsive force, and it starts to draw the atoms closer to each other. The potential energy decreases, right? Their position is that they are closer to each other. So that's why they are lower in the picture compared to here. The potential energy at this point is a little bit lower than when they are just individuals. As that attractive force continues to draw them together closer and closer, their potential energy continues to decrease. And so that's what this is representing here, is that they are getting closer and closer together. The repulsive force is also increasing. As those electrons in the valence shells get closer and closer to each other, they are going to repel more and more. So the attractive force is still there, drawing them together, but my repulsive force is getting bigger. And the potential energy, which has to do with their position in relation to each other, they get closer and closer together, so the potential energy decreases. Then we have this position here. In this picture, it's important that you drew the valence shells as overlapped a little bit. If you didn't, you need to make sure that you do. And what's happening here is that the forces, that attractive force drawing them together, and the repulsive force between the like-charged electrons is equal. We have reached a point of equilibrium. The outer energy levels of the two atoms overlap a little bit. This is the place where the shared electrons can exist, is in that region where those energy levels have overlapped. The potential energy is at its lowest. See how far down on the y-axis we are? This is where we have the covalent bond. The word covalent comes from the prefix co, meaning from two separate places, but now together, and valent, which refers to the valence shell. The electrostatic attractions hold the atoms together, and that's the attraction between the positive nucleus and the negative electron. It is the strongest kind of bond. This is what we call a molecule at this point. If the atoms were to get any closer together, if there was even more overlap, like what we have shown here, so this has to show more overlap of the valence shells than you do here, then those repulsive forces really kick in. Not only do you have electrons repelling, but you also have the positive nuclei getting close enough now that they also repel. And the potential energy increases a lot. Notice that this is a much higher potential energy than any of the other positions. And so what happens is that a molecule, the distance between the nuclei does not necessarily stay just one fixed distance. It actually vibrates back and forth. So it will get a little too close, and those repulsive forces kick in and push it apart. And then if it gets a little too far apart, the attractive force is a little bit bigger, and it pulls it back in. And so this is like the average distance here. But in reality, the distance between those nuclei It actually vibrates back and forth a little bit. This is going to be an essay question on your test when we get to that point. You will have to draw the picture and explain each part, A, B, C, D, and E. So you might want to mark that, and that is something that you could start working on in preparation for the test.
As in like fill in the blanks or write the whole thing?
No, you will have to write the explanations for yourself. It does not have to be complete sentences. It does not have to be word for word, but you do have to have all the parts there. So for example, in letter A, it's important that you mention that they are non-metallic atoms. That is an important word in there. Those sections like B and D that have kind of multiple sentences, you could bullet point those if you wanted to. So the bond length is the distance from the nucleus of one atom to the nucleus of another when they are covalently bonded. So if you imagine the nuclei to be in the center up here, that distance between them, that's your bond length. If the nucleus is in the center, the bond length would be the distance from one nucleus to another. The bond energy is the energy that's required to break a covalent bond and turn them back into neutral, isolated atoms. On the chart that you were given, you used one side of it yesterday for your quiz. Now we're going to look at some of the charts on the other side. So if you'll pull that chart out. We actually have both of those quantities, the bond length and the bond energy, is on one chart. Your bond length is given in measurement of picometers, because the distance between two nuclei is going to be pretty small. And the bond energy is given in terms of kilojoules per mole. This tells you what kind of bond you are looking at. It may represent an actual molecule, or it may be just a bond between two atoms that's in a bigger molecule. So this is a hydrogen-hydrogen single bond. This is the bond length of it. And this is how much energy would be required if you were going to break that bond and just have two individual hydrogen atoms. And so we have all sorts of different bonds listed. I've added some that you'll be needing a little bit later. And the bottom chart is also bond length and bond energies, but we have some multiple bonds there, double bonds and triple bonds. Okay. So this will be one of the charts that you will be using next. The component of a covalent network are the atoms. Okay, that's what make them up. And the electrostatic attraction is between the positive nucleus of one atom and the negative electrons of the other atom. That's the nature of the covalent bond. A lot of times it's described as, it's the sharing of the electrons. Well, it's actually that attraction. Remember we talked about how in order for a bond to be created, there has to be something that's positively charged and something that's negatively charged that can attract each other. And that's what's attracting. The lattice structure is referred to as the covalent network. An example of this is diamond. The nature of this bond, it is a rigid bond, right? If I push on it, it doesn't bend. Okay, it's pretty rigid. And so what are the properties of this compound because of the nature of the bond? Because of the fact that it is rigid? It does not, okay, remember going back to that front page on your packet, we talked about being able to conduct electricity. To be able to conduct electricity, you have to have free moving charges. Does this have any charged particles that are able to freely move? No. So it does not conduct electricity as a solid. Now for ionic compounds, we said that it did conduct electricity when it was melted. What if I melt a diamond? And yes, that's possible to do. You can melt a diamond. If it's melted and now those atoms can move around, do I have charged particles that can freely move? No, I still don't. Atoms are neutrally charged. So even melted, it is not going to conduct electricity. Then we talked about whether it's shiny or dull. And we said to be shiny, it has to be able to have electrons that can move energy levels very easily. Is that going to be the case in our covalent network? No. All of the electrons are localized. They all have a very specific nucleus that they belong to. So diamonds are actually dull in color. What you think of as being like a glittery diamond, that is not shininess. That's due to the, when it's polished, being able to refract light. And that's a different property. It is possible that you could pick up a diamond and you don't even realize it's a diamond. It would kind of look like just any other rock. They don't look clear and sparkly unless they are cut and polished. Conducting heat. To be able to conduct heat, we have to be able to transmit a vibration easily. With those rigid bonds, can we transmit a vibration easily through there? No. So they do not conduct heat well. If I take a hammer to a diamond, can you hammer it out into a thin sheet? No. So diamonds are brittle. Do not confuse hardness with brittleness. If diamonds were not brittle, we could not cut them into the different shapes with those different facets on them. It is possible to, and people that are good at this make lots of money at taking a diamond, they examine like where the flaws are, and they are able to cut it kind of like with a hammer and chisel and make it break along lines to make those flat surfaces or those facets, and then they shape it into diamonds that we use for jewelry and things. So it is brittle. We can make diamond dust. Right? We cannot make flat sheets of diamond, though. And then we have, on the next page, talking about the strength of this. These are the strongest of all types of bonds. And so what kind of properties would we see because of this strong bond? We would notice that the melting point and the boiling point would be very high. And in fact, these substances have the highest melting points and boiling points of all the substances. They would have very high heats of fusion and heats of vaporization. Remember the difference here, melting point and boiling point refer to the temperatures at which those changes of state occur. Heats of fusion and heats of vaporization refer to the amount of energy needed to make those changes occur. For these kinds of substances, we tend to use bond energies as our way to interpret the strength. So if we go back and look at that chart, on this middle chart, which one is the strongest bond? We're looking at the bond energies. Which one is the strongest? Between the hydrogen and the fluorine? Because it takes the most energy to break it apart. So that makes sense, right? If it takes a lot of energy to break it apart, it must mean that it's stronger. Do you notice any pattern between the kind of numbers we have for bond energies compared to the kind of numbers that we have for bond length? What do we notice about those things that have pretty high bond energies? What kind of bond lengths do they have? Sam?
Some of the higher energies, higher lengths have higher energies, or small energies.
Okay, so the ones that have the highest length, like this one, have lower energies. The ones that have the lower lengths, the shorter lengths, have the highest energies. Think about a stick. Isn't it easier to break a long stick than it is to break a really short stick? You know, if I take this pencil and if I want to break it in two, this isn't going to be very difficult. But if my pencil is only this long, then it's going to be harder to break in two, isn't it? And that's what we notice with bonds. If it takes a lot of energy to break them, then those are the shorter bonds. Okay, they're held together more tightly, more closely. So for covalent networks, we use bond energies as our way of interpreting which bonds are stronger. They're all strong, but obviously some are going to be stronger than others. And then we have hardness. Remember, hardness in scientific terms is the ability to be scratched. It means if I take something and I drag it across here, if I want to leave a scratch, that means I have to break some of those bonds. Well, if these bonds are really, really strong, am I going to be able to scratch it very easily? No. Covalent network substances are the hardest substances. They are not scratched very easily. So remember, there's a difference between thinking about something in terms of hardness compared to brittleness. Okay, so that was covalent network. But covalent bonding can happen in a different way as well, and it results in what we call covalent molecular bonding. This also occurs between elements that are both nonmetals. Sometimes when atoms share electrons, they create small units, and then those small units organize themselves into a lattice structure. The small units we call molecules. So for example, I can have a molecule, and this represents the covalent bond between these two atoms, and another covalent bond over here. But then this exists as a unit by itself. And then here's another one. I lost one of my atoms off of it. Okay, there's another one. And here's another one. Okay, and so those individual small units we call molecules. But then these molecules can arrange themselves into a pattern and have an interaction between the molecules. These represent water molecules, right? Oxygen and 2 hydrogen. And this represents what they look like. Well, we'll do it out here. It's too big for under there. This represents. Okay, so what we're going to look at is how we can represent these molecules. And there are some, I said rules, but they're really more like guidelines. Because it's chemistry, it's like, rules. Often there are exceptions. But for the most part, for the ones that you're going to be making, atoms want to have an octet in its valence shell. And remember, that means it wants to have 8 electrons, 2 in the S, 6 in the P. Here are some exceptions that you'll need to know. Hydrogen and lithium, they are stable with just 2 electrons because their valence shell is the first energy level and it can only hold 2 electrons. These are really small atoms. Beryllium is stable with 4. Again, it's a pretty small atom, and so it can be stable with fewer than 8. And boron is stable with 6. Okay, so those are the exceptions that you'll need to know. Everything else should wind up with 8. There are atoms that can have more than 8, such as sulfur and phosphorus. Once we start to look at elements in period 3, they can actually have 10 or even 12 electrons around them. We're not going to deal with that scenario for the most part. Molecules tend to be shaped like wagon wheels, where you have a central atom and then you have other atoms hooked onto it around. Okay, so this is kind of like a wheel with the hub in the middle, and then you have the spokes going out. Not too much like a train. We actually do have molecules like this, but they are organic molecules, and you're not going to be working with those for the most part. A couple real small ones, but that's it. If you take AP Chem, you learn about this kind of molecule. You do some organic there. And usually we don't have triangles either, for the most part. There are exceptions, but for the molecules that you are doing, the very smallest, simplest molecules that you'll be doing, you're not going to have any triangles. The central atom is the element that is least electronegative. And on your paper with your charts, that's the one that's at the top. I gave you a copy of the electronegativities chart so you could have that easily at hand. However, hydrogen, even if it's less electronegative, it is never in the center. If you have carbon as one of your elements, it will always be the central, even if it's not the least electronegative. The element hydrogen and the other group 1 elements and group 17 elements, they tend to only form one single bond to one other element. And this will make more sense once we actually start doing this. The elements in group 2 and group 16, they tend to make 2 bonds, either 2 separate single bonds or a single double bond. And group 15, they tend to make 3 bonds, either 3 single bonds to 3 separate elements, or a double bond to one element and a single bond to another element, or it can make a triple bond to one other element. And group 14 elements, they want to have 4 bonds, either 4 single bonds to 4 separate atoms. It could be 2 doubles, it could be a triple and a single, but we never ever have a quadruple bond. Okay? Never ever have we seen a quadruple bond. Okay, so we're going to look at applying these rules using our electron dot notation that we learned earlier. And whereas before you were just given the elements, you will be given the molecule. So the molecule that we are doing is PF3. Do you have this in your notes packet? Okay. Make this a little bit bigger. So the first thing that you're going to do is you are going to draw the electron dot pictures for each individual atom. So PF3 means I have one phosphorus. It has 5 valence electrons, so I'm going to represent those. And then I have 3 fluorines. Each fluorine has 7 valence electrons. Then you are going to determine the central atom. And we can look up the electronegativities on our chart. And we know that fluorine is a 4 and phosphorus is a 2.1. So phosphorus is our central atom. It also turns out that the central atom is usually going to be the one that has the most number of single electrons. This has 3 single electrons, doesn't it? Whereas these only have 1. So this is going to be your central atom. That's another way to kind of determine that. And so we draw the phosphorus, and then it's usually where we have those single electrons that's where they're going to plug in and share. So this phosphorus, its single electron is going to share with, this fluorine and its single electron will share this single electron from the phosphorus. And this is where you kind of have to rearrange where you put your pairs and singles. I tried to make my phosphorus atoms be the filled-in circles for the electrons, and the fluorine are the open circles. Shared electrons are the ones that exist between the 2 symbols. That's how we know that these are the shared ones. So this is a shared pair. These out here are unshared pairs. Okay. It is a pair of electrons, but it's not being shared. Okay. So now, and you don't have to draw this if you don't want to, but if we look at each element, phosphorus now has 8 electrons around it, and so does each fluorine. If you look at each fluorine. Remember, the shared pairs get claimed by both. So the phosphorus counted those 2 electrons, and so does the fluorine. So each fluorine now has an octet. You will not have to show this in any of the work that you do. Okay? I'm just trying to show you how to check for that octet. It is possible for atoms to share more than 2 electrons, and you would show that. You could put 4 electrons in there, and that would be a double bond, and you just put all 4 of them in there like that. A simpler notation is to represent only the shared electrons. This is called a structural formula. like this. And it can be oriented this way, or it can be oriented this way. Make sure that you kind of read through this part of your notes there. Okay. Your assignment then, it's right there on your paper. You are going to do Lewis dot diagrams for the following molecules, and you will do them on your own paper. You will be doing, start with this step where you do the individuals, and then do this step here, and then finish with the structural formula. Do it in pencil, because you may find that you need to move stuff around or change stuff, and it's a lot easier if it's in pencil. Make it big enough to see. Don't make it real little. Okay? It's not the time to